Let's continue our discussion on simple linear models. We ended our last episode with a little bit of a discussion of the population regression model, its format, what the parameters tell us, how we interpret them. They have important interpretation. Most of the time they have practical business interpretation. And they essentially boil down to being the whole essence of why we do this regression thing at all. So we have a sample regression model. Sample just means there's estimates. Okay, so you'll notice how we've gone from the Greek letters beta 0 and beta 1 to just regular letters of B0, B1, and YI stays the same. And then EI for the errors, because these are now estimates. This B0, B1, those are just placeholders for values that we've actually determined. Okay. This model, anytime we have a model, you'll see little subscript i's everywhere. That just means there's a specific observation, and this specific observation equals to this equation. Okay, B0 plus B1 times by X. Xi is in this case, but because X itself is a value for the exogenous variable specifically related to a particular dependent variable or endogenous variable. Okay, and then there's an error because there's, with a particular estimate, because we're talking about individual particular estimates in this particular regard. For a particular individual estimate, there may be the relationship will hold, but there will be idiosyncratic factors related to that individual that may make that individual observation slightly different than the average or typical observation. We'll see some graphs, and that'll be a little less abstract, but that's a very important point. So B0, B1, EI, they're sample estimates for those respective Greek letters. So there's actually particular numbers that you'd plug into this. So for instance, if you were to report the sample regression line, you'd have an actual value for B0. You'd have an actual value for B1. It's just a placeholder in this particular regard. Okay, now moving on to the population regression line. Once you say line, it means you're dealing with average values, hence why we see the expected value operator here. You see expected value with the Y in the square brackets. That means basically we're finding averages. And once we find averages, you notice that the error term has now disappeared. And that is because the average of the errors is considered to be 0. Okay, it's one of the assumptions we will see for the simple or for linear regression model is that the expected value of the errors is 0. They sort of cancel each other out. So we still, with the population regression line, we still don't know what beta 0 and beta 1 is. We know they exist. We suspect that there's a relationship, but it's unknown to us. Hence, again, the Greek letters. This expected value operator here, extremely important. Okay, if you don't have an error here, you have to have a line, right? And lines represent averages, believe it or not. Right? So lines represent, especially in statistics, represent the average value, or represent average values, I guess. So the expected value operator, very, 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 very important. Sample regression line, sometimes we can use the expected value operator as well. Tradition often has it where we put a little hat on there. It means the same thing. Okay, so Y hat means estimate. Okay. Estimate, and then here's our estimate. Notice again, it's like an expected value. Expected value of the E's or expected value of the errors is 0 as well. Okay. But as was the case with the sample population line, with the population regression line, as was the case with, I'm going to go back here, the sample regression model, B0, B1 are actual numbers. Okay, so that wraps up that little discussion. Again, like the expected value operator was important before, The little hat is important now. Okay, so we have styles or flavors of linear relationships. Sometimes the independent variable and the dependent variable are positively related. That just means as the independent variable goes up, the dependent variable also increases. Okay? The starting point of the regression line, basically where that y-intercept is the slope, just like it was when you're dealing with basic math in high school. Negative relationship just means as the x goes up, right, goes from the left to the right, the line goes down, i.e. the expected values for the y's are dropping. And so we'd see a negative slope in that regard. So beta 1, in this case, would be a negative number. An increase by 1 unit in the x would result in some sort of drop in the average value for the y. And then, and that's fine. We don't care. Positive relationship, negative relationship. They're both good to us, right? Knowing what to do to increase a performance indicator is just as important as knowing what not to do, right? Knowing what would decrease it so that we could avoid that as much as we possibly can. So positives, negatives, those are good, right? Those belong in the model. They're important to have. They both give us important interpretations, and they both provide us with important information. The no relationship, well, I mean, that's less satisfying. It tells us that, at least it tells us that this x, whatever that independent variable is, doesn't impact the y. That could be important. It could be interesting, too. We may think that there was a relationship between the x and the y. Turns out, no such relationship. So that's useful as well. We can't really use it in a predictive capacity. We don't know what to avoid or what to add. All we know that is this thing doesn't matter, which can be important too, because maybe it'll tell us, well, don't worry about directing resources to influencing whatever this independent variable is, because it's not going to have an impact on the thing that we care about anyway. So again, all has important informational value. It's just in different ways. Okay, so let's just kind of deal with this example here. And we have a graph, and we have a line. And basically what this relationship is we're looking at the relationship between movie revenue and tweet rate. Okay, so tweet rate being described as the average number of tweets referring to the movie per hour 1 week prior to the movie's release. Now, our first step is we consider the question, can the straight line, does a straight line somewhat describe this relationship? Because clearly, if the relationship is not linear, then doing linear regression on a nonlinear problem is going to lead to perhaps misleading results. Now we look at this, and by linear relationship doesn't have to be perfect. They don't have to all line up really tightly on a line. We do note that it does follow an overall trend. I know having the line there kind of can bias you a little bit, but gives us a little bit maybe guidance that it's probably linear. There is a slight concern area here as we look at this, and this will be something we won't deal with for quite a while, but there's this thing called non-constant variance, and that's just where the spread for certain ranges of the data are wider than for other ranges of the data. For instance, we see a pretty tight kind of clustering along the line at the lower levels of tweet rate and the lower levels of revenue. And then it kind of starts to spread out a little bit more. Now, the caution on that is that there's not very many data points, so it may not be a big deal. But this wider spread at some levels of tweet rate than others is a potential concern. We'll learn how to test for that later on. But these are just things that are jumping out right now. But we see that, the overall, there's a trend. Tweet rate goes up, revenues go up. It's not bouncing all over the place. It doesn't look like it's completely random. And so it appears that things can be described by a linear line. couple things we'll note is that we do have an estimate, right? Now, I know Excel doesn't put the little expected value y on there or the y hat on there, and that's on them, okay? But we recognize that this would properly be described as a y hat. And we see the slope of 0.0788. So that just means that an increase of 1 unit in x. Now, what is 1 unit in x? Well, that would be an increase by 1 for the average number of tweets referring to the movie per hour 1 week prior to the movie's release. So I get that that's a mouthful. But 1 unit increase in that average would lead to a 0.0788 million increase in revenues. Now, nobody talks 0.0788 million, so you would convert that into money. And so what did that be? We move that 1, 2, 3, 1, 2, 3. So it looks like about $79,000, $78,800. Okay, and that's how regular people talk. Okay? So an increase by 1 in the average number of tweets referring to the movie would result in an increase in revenue of about looks like to be about $78,800. Okay. Now, what happens if there's no tweeting? Well, then our average value of our average revenue would be the intercept, which is 1.15, so about $1,150,000. So 1.15 million. Nobody's tweeting about this thing. Okay. Now we have the all-important errors. This looks like errors. Who cares about errors? I mean, look at the graph, man. We're predicting stuff. We got a model. We're able to forecast revenues. Errors, man. You're just kind of bringing us down. This is like killing the euphoric moment of modeling. Well, there's a lot of information to this error. Okay, and all error it's a simple calculation. But we use it to diagnose so many things about the validity and the accuracy of our model that this simple little formula does so much for us. We have the actual observation, which is yi, minus the expected observation, which is y hat. Now this expected observation y hat, that's just the line, right? So the difference between the actual observation and the line, which is what we would expect the observation to be, the line just depicts our expectations, is the error. Okay, so the difference is the error. So let's go back to our graph, and we see for some of these it's pretty small, right? Like between this one here and the line, that's error. So what caused that error? Well, we had 3 causes for that error, right? Omitted variables, which we suspect that there are other things driving movie revenues other than the tweet rate. Right? Who's in the movie, whether you can actually go to a movie theater. I mean, we won't deal with the actual go to the movie theater part, but lots of things that impact a movie, not just tweet rate. And so we could have some measurement error. I mean, that could be possible. Just the gathering of people typing stuff into cash registers and point of sales, punch in the wrong movie, forget to punch in the movie, things like that, and just random error. I mean, hey, why did this movie become hot? I don't know. There's always a movie or two here and there that just all of a sudden come out of nowhere and become cult classics, and you go, oh, I never saw that. Nobody saw that coming, right? I remember watching Deadpool for the first time. Basically a movie that had been like cast aside, and the movie company really didn't give a crap about it, and it hit home run. It did really, really great. Okay, so those errors tell us a lot, and they're just the distance between the actual observation and the line. Right? Look at this one, right on the line. Got that one labeled. Now note that each one of these dots represents a specific movie, so there can be things related to that specific movie that are causing it to deviate from the line. Look at this one, really underperformed, right? Something specific to that individual movie. People are tweeting about it, but nobody went to see it. Could be that it sucked really badly, right? And everyone's just tweeting about how bad this movie was, and so nobody went. So each individual dot tells its own story. We just know if there's a story to be told or not. And for some of these, there's a potential story to be told. Why is this one so much higher than we would predict? These ones are along the line, so maybe this model here does a pretty good job of giving us an indication as to our expectations for this movie's performance. A lot of cool stuff here. Okay. Now, but before we get too crazy about the min and the capital sigma here and the subscripts and the I is 1 to n and all that kind of stuff, all this slide is intended to show is our style of linear regression calculation is called the method of least squares. Okay, so least squares, least means small, right? Min, minimum, right? So small squares, squares of what? Squares of the error, right? We want to minimize error. Well, that makes sense. Anytime we're doing a model, we're doing a forecast, yes, there's going to be error. It's inevitable. We saw 3 sources for error. One of them is just random stuff, just random stuff. And how do you predict random stuff? It's really hard to predict random stuff. How do you bring non-quantitative items into our model? Well, that can be kind of hard. We're going to try, right? We got some tools that we're going to try, but you're never going to nail it just perfectly. It's just not going to be hitting it out of the park every single time. So we're trying to minimize those squared errors. Now we know that the expected value of the errors is 0. So just adding the errors up isn't going to do us any good because you're just going to get 0, right? I mean, big deal. Whoop-de-doo. Whereas we square those errors and then we try to make that number as small as possible. Okay? And so that's henceforth why we call it the method of least squares linear regression. We're trying to minimize the squared errors. There's other modeling you can do that's not focused so much on the minimizing the least squares. That's one technique. It's by far the most popular technique, but it's not the only technique. And when you take Management Science 352, we'll actually be able to optimize some of our forecasting models. They won't be linear models, but we will come up with optimal non-linear models in Management Science 352 where we don't have to minimize least squares. We can minimize something else, some other error measure. But this one is the most used, the most prevalent, and that's the one we're going to focus in on. Okay, so we now see a little bit nicer graphs rather than me pointing with my little cursor here. But now we see there's the distance between a particular observation and the line. Another word for that error is called a residual. So when you look at Excel in a lot of stats packages, you'll see this. Oh, look at the residuals. Do you want a graph of the residuals? Do you want a calculation of the residuals? They're just talking about that error. That's all residual means. Just a little residue, it just means that leftover part, which sometimes is just, we refer to it as that leftover goo is the error. Okay. Now again, what's driving that residual? It can be a whole story in and of itself, like we're talking about here with this movie, with a high tweet rate but a very low revenue. What happened with that particular movie? Right? Clearly something specific to that movie occurred, but not necessarily indicative of the overall trend between, or the overall relationship between tweet rate and movie revenue. And hey, above the line is great. What was it about that particular movie that it outperformed? And sometimes when they do modeling with stocks, you'll see this kind of relationship. Why is it that this particular company outperformed? Right? What is it specific about this company? And maybe that bears more examination, that there's another variable out there. Because remember, one of the sources of error is omitted variables. Is there's a variable that we're missing, and so we can look at that particular movie or that particular stock and see, okay, what did they do differently what happened to them differently that's causing this deviation? And then we can then see if maybe we can incorporate that into our model as another variable. So those residuals really, really have a very, very useful or a high usefulness. Okay, so the slope for the estimated regression, I'm going to flash it up here for a second. We'll just finish up our little segment here. Now, we're not going to do grunt calculations. We recognize we're in applied field. We want to know that this is the formula for determining the slope. We're not going to actually go and grunt out and pound out these formulas. But what we do need is to understand what is going on when we're calculating the slope. When we're calculating the slope, we are taking a particular observation, a particular value for x related to a particular observation. We are taking a particular value for y for that same observation. Notice I is the subscript for both. Comparing it to the x to its average x, comparing y to its average y. Negative is just another way to say we're comparing it to something. Okay, so taking the difference and comparing can be synonymous. So if x is above average, this is a positive number. If at the time that x is above average, y is also above average, so y minus y bar is a positive number, then they're both going up at the same time. Same story if x is a negative, i.e. it's below average, and y is negative, i.e. it's below average, then they're below average, their respective averages at the same time. And so that again says they're positive. It's a positive relationship because when one is negative, the other is negative. When one is low, the other one is also low. So we can kind of see that they're moving together. However, if x is above average at the time that y is below average, then that suggests they're going in different directions because this numerator would now be negative. We'd have a positive number multiplied by a negative number, and that would be a negative number. And so now they're moving in opposite directions. And hence, we would have a slope that was negative. So when x is above average and y is below average, that's a negative relationship. We would have a negative slope. So the formula gives us... and formulas in general and equations in general really give us a very abbreviated representation of what the relationship is. Now, because it's very abbreviated, it can feel very overwhelming because it's really tight. Look at I've spent 3 minutes talking about this one formula and the relationships that it shows, but yet it's one not very complicated formula. And so it can really, when you think a picture tells 1,000. Picture, what was it? A picture represents 1,000 words. Formulas, same kind of idea. They can represent easily 1,000 words as well. Okay, but we want to have that gut sense for how that relationship is because we want to be able to interpret things, and part of that interpretation is to get a really full-bodied understanding of what that number is representing, how that number came about, how that number was calculated, so that we have a really good idea that if x is above average, what does y do? Is it above average or is it below average? And just understanding those relationships so that we can talk about them comfortably and confidently, especially confidently. Okay, when we come back, we'll continue on with our journey into simple linear regression.